Hello everyone. Thank you for watching this video presentation of our paper on characterizing data streams using FPGAs. My name is Monica and this is joint work with Thomas from Accemic Technologies and Gustavo from ETH Zurich. In this paper, we focus on the problem of stream analytics, which is to extract meaningful information from a stream of data, for example, as it is traveling through the network or stored in the memory. What kind of meaningful information do we want to extract from a data stream? Besides basic statistics such as maximum, minimum, average values, analysts are also interested in more complex metrics such as cardinality, frequency distribution, and second frequency moment. It is often the case that multiple metrics are needed in order to fully characterize a data stream, and not just one. For example, for a skewed data set, we may want to compute both the second frequency moment that indicates the data skewedness, and we may also want to identify the most common items using the stream items frequency metric. The naive approach to computing multiple metrics would be to perform several passes over the data, one pass for each metric. But this approach would have a large compute overhead. Instead, our main insight in this work is that multiple metrics can be efficiently computed in a single pass over the data. We do so using different compute platforms, high-end server class CPUs and FPGAs. We focus our design on these two platforms because each of them comes with their own interesting trade-offs between strengths and weaknesses. The CPUs offer a high level of programming generality with high working frequencies, but their architecture is not natively built for streaming, whereas the FPGAs have a reduced level of programming generality, an inherent level of parallelism, and are suitable for streaming applications. To obtain these data summaries over very large data streams with number of elements in the order of billions often implies a trade-off between algorithms' time and space efficiencies and the accuracy of the results. In this work, we focus on a class of approximation algorithms, also known as sketch algorithms. We propose to use hyperlog to estimate the stream's cardinality, count-min to estimate stream's items frequency, and fast Hdms to approximate the stream's second frequency moment. Hyperlog is a hash-based algorithm that estimates the number of distinct elements in a data stream by monitoring the maximum number of leading zeros in the hash value. This means that if a maximum of x leading zeros has been seen, one has probably processed 2 to the power x distinct elements. This approach can lead to large errors in overestimating the cardinality if in a data stream with few elements we encounter a hash value with many leading zeros. Such an error can be overcome by creating an array of partial cardinalities and by computing the overall estimated cardinality as the harmonic mean across all these partial cardinalities normalized by the number of array indices. CountMin is the second hash-based algorithm that we include in our systems kit, and it estimates the occurrence frequency of data items in a stream. CountMin is similar to, but different than the Bloom filter. Similar because it can also tell the membership of an item to a data stream, and different because more than the membership, it can tell the number of times a data item appears in a data stream. CountMin never underestimates, but it may overestimate its return value due to hash collisions. Its underlying data structure is a matrix, and the elements of each row get updated with a +1 when the column index is the same with the hash value of the hash function that is associated to the row. If hyperlog returns only a scalar value, estimating the cardinality of a data stream, CountMin will return the entire data structure that can be later queried by the upper layers of the system. FastHGMS is the third hash-based algorithm we include in our systems kit, and it estimates the second frequency moment of a data stream. Its underlying data structure is similar to the one of the CountMin algorithm, but different because it uses one more bit in the hash value in order to determine if a 1 is added or subtracted to the counter that resides in each column. Similar to hyperlog-log, fast Hdms will return a scalar value that represents the estimated value of the second frequency moment. Since all three algorithms that I have previously presented you are hash-based algorithms, our main idea is to hash the input value only once and use the obtained hash value in order to update the underlying data structure of each algorithm. In this block diagram, you can observe the unidirectional design of our system, SKIT. The same architecture principle is used to design the software implementation for the CPU and the hardware implementation for the FPGA. Let me walk you through the data flow of the design. Each input data item is hashed once in the hashing phase. The hash value is afterwards distributed to each partial sketch and used to update the data structure behind it. These actions take place in hash slicing and sketching phases. After consuming all the input values, SKIT triggers the merging of all partial sketches during the associative reduce phase and generates the output results for each sketch algorithm in the evaluation phase. In the following, I will present you our system's evaluation for the software implementation we did on the CPU and the hardware implementation we did on the FPGA with data residing either on the main memory of the CPU or coming from the TCP/IP network. For the software evaluation, with data residing in the main memory of the CPU, we have benchmarked each algorithm individually. Hyperlog-log in red, CountMin in purple, and FastAGMS in brown, and all three algorithms working together under software skate in yellow. On the y-axis, you can observe the throughput in gigabytes per second, whereas on the x-axis, you can observe the number of threads allocated for compute. It can be seen that software skit gets to a maximum throughput of around 4 gigabytes per second for 40 threads while analyzing 1 billion samples of 32-bit integer values. Allocating further resources for compute doesn't improve further the throughput performance. This implementation is used as a software baseline for the comparison with the FPGA implementation. For the hardware evaluation, data resides initially in the main memory of the CPU, and the FPGA behaves as a coprocessor being connected to the CPU via the PCA communication bus. If for the software implementation, the level of parallelism is given by the number of threads, for the FPGA, the level of parallelism is given by the number of pipelines that are working in parallel. The throughput performance with different number of pipelines on the FPGA is represented in different colors on the graph. This time, on the x-axis, we represent the number of elements that can be sent to the coprocessor from the CPU. It can be observed that with 9 and more pipelines, SKIT can saturate the PCI Express bandwidth that is observed within Xilinx QDMA shell, reaching a maximum of 8 gigabytes per second throughput. For the third part of our evaluation, we compared the behavior of the CPU with the behavior of the FPGA when data comes from the 100G TCP/IP network. For this software implementation, we allocate one thread for each network reception connection, and for each receiving thread, we allocate 4 threads for sketch computation. For the FPGA implementation, we allocate the same number of pipelines as for the previous experiment, with data coming from the main memory of the CPU. Represented in green, it can be observed that the CPU can maintain the 100G TCP/IP throughput with 16 threads being allocated for data reception and no sketch computation added on top. When the sketch computation is added on top of the communication, the CPU performance drops to around 4 gigabytes per second, as it is illustrated in pink. In purple, it can be observed that the FPGA can maintain both the 100G TCP/IP throughput and sketch computation with 16 pipelines being allocated for sketch computation. The messages I would like you to take away from this presentation are the following. FPGAs are a good candidate for low overhead data analytics. They can efficiently extract information with only a single pass over the data and can saturate 100G TCP/IP communication links. Finally, it is important to keep in mind that the interaction between the communication kernel and the computation kernel is important in order to achieve high performances.